예수이, 야, 형주, 정재익, 정희준. 이제 눈을 맞추잖아, 이름 나오면. 아, 희훈. 한 끗 차이네. 그 다음에 유성훈. 유성훈 학생. 정형록. 영인. 박성우 학생. 박세진 학생 있고. 아, 이성규 학생이 학회 가서 아직도 결석이구나. 오케이. 그럼 다 왔네. 오케이. 그럼 됐고. 그 다음에 오늘 뭐를 해야 되죠? So what do we need to do today? 내가 파일을 하나 안 갖고 왔네. 아, 파일을 하나 안 갖고 왔는데. 아, 저기다 적어서 하면 되긴 하지. 다시 갈 필요는 없겠다. Alright, so let's get started. And where is the info theory directory? Which is right here, note number 2. Okay, and where were we last time? We talked about Jensen's inequality, and basically one thing that you need to learn was definition of the convex function. Right? If you know the definition of the convex function, it's easy to derive this one, right? Expectation of a function of expectation. For convex function, inequality goes this way. And if it is a strictly convex function, equality part, if and only if x is a constant. We talked about that. And then some of you have asked me a question. What about the continuous distribution case, right? Random variable have a two part, mapping part. We talked about the continuous mapping, but entropy is about distribution, right? So who was that person that asked me that question the other day? Raise your hand. Continuous case는 어떻습니까? 그거 물어봤었죠? 그 이제 뭐 아직도 질문이에요, 그게? 네? Continuous random variable 할 때 우리가 이제 so those continuous random variable that we will discuss later on include the Gaussian functions and uniform distribution and the exponential distribution maybe. All those things are well behaving distributions, so obviously it applies. This one applies. But I was talking about the practicality of because we have a limited amount of time, basically, and if you consider Cover's proof, it is only about discrete cases, right? Discrete cases, and then I told you that discrete cases are enough, right? When you want to extend it to continuous function, you just need to make use of the limit theorem, and then you do the quantization, make it simpler, and then let the the number of samples go to infinity, and then make the interval smaller. Then you get continuous integration and so on. And but that question was, I think, was a good question, and the note that I was trying to bring this morning was about this book. This book was the mathematics textbook that I learned in UCLA when I was doing mathematical minor, right? And then it shows exactly that. So I forgot the page. So I'll send you the picture of this page, so that if you have a continuous distribution case, what type of a proof should be done, right? Because Carver and Thomas only talks about discrete cases. Right? But what I'm saying is that is good enough for electrical engineer. If you want to extend it to continuous case, right? You just need to make use of this direct delta function so that you do quantization, sampling and quantization, that will be done, right? But this textbook does exactly that, right? But with much more lemmas and theorems before you get to that point, right? But I don't want to discuss too much of that, right? So this applies to continuous distribution case as well, okay? But in this course, because we are going to design our own random variables, and then when we use this random variable for entropies and mutual information mostly, and the continuous random variable we will deal with mostly for the noise case. So in this particular case, the Carver and Thomas proof of discrete cases is good enough. Okay. All right. Having said that, another thing that I want to take care of, but I forgot to bring my file, so I will have to do it on the board. Okay. So since you guys have submitted homeworks, we need to talk about the graders. Okay, so we will have 8 homework set. Now it is the time to decide who will do homework number 1, homework number 2, 3, 4, 5, 6, 7, 8. And this person is doing the leader role, so initiating the communication between you guys and the rest of them, and the helper. So 2-person team, okay? So raise your hand. Maybe we go, yeah. Which one do you like to select?
I will go first.
This one? Your name, initial please. 지훈?
Yeah.
지훈? 정지훈? Okay, good enough? No good? You don't like it?
I like it.
All right. So how about helper? How about this one, please? 이름까지 영어로 할 필요는 없구나. Okay, this part, helper. 정민석 학생. 자, homework 3. 이거 처음 해봤나? 요거, 뭐 할 거야?
제가 하겠습니다.
요거 할 거야? 이름 한 번만 더. 두영서? 이게 또 학부 학생들은 그레이딩에 민감해가지고 어떻게 학생 보고 채점을 하라고 할 수가 있습니까? 하고 막 밖에 나가서 시위하고 그러는 거 아니야?
SU로서 상관없습니다.
어? 뭐라고?
SU로 수강 신청해서 괜찮습니다.
아이씨, 이거 안 되는데. SU요? 안 되는데, 이거. 학생 뭐 할 거야? 한 번만 더. 맞아, 유기현 학생. 이거 외워야 되는데. 잘 안 외워져. 호목 넘버 4. 호목 넘버 4, please. 저기 먼저 들었어. 정재희 학생이 리더. 그 다음에 김영주. 그 다음에 5번. 오케이. 6번. 응? 조영인. 그 다음에 유수민. 7. 안 한 사람. 응. 박세희 학생. 진인가? 아. 그 다음에 헬퍼는 누구로 쓰시겠습니까? 안 한 사람. 아직 한 번도 안 한 사람. 다 했나? 팀이 있구나. 아, 그러면 지금 출장간 하고 해야 되겠다. 거기서 봐. 그 사람 이름 좀. 예? 정형로. 아, 이름을 다 외워야 되는데. 왜 이렇게 이름이 안 외워지는지 모르겠어. 그 다음에 유성훈 학생. 그 다음에 그 출장 간 학생 이름이 뭐더라? 출장 간 학생 이름이 네? 이성규. 아는 사람이에요? 오케이, 이거 사진 좀 여기 형제야 사진 좀 찍어갖고 나한테 좀 보내줘라. 오케이, 그러면 한 가지 해결했고, 우리가 카톡방이 있으니까 so we have a 카톡 room, right? So once you receive the homework solutions, within 2 days, please, right? Type up the best homework manual for all of us. And then once you type up the homework manual, post it in our 카톡 room so that everybody can see it. Oh, your best solution is no good, so someone can challenge, right? So your solution is no good, right? My solution was right? So you have this challenging period, and then no one is making any opinion about it. Then you can just start grading it, and mark the your homeworks, right? And probably in the scale of 4. If the person didn't do anything at all for that particular problem, 0, right? And then fair, 30%, right? Good, 60%, excellent, everything is perfect. Then there is 1 point for each problem. Okay? Okay? Sounds good? I have typed them up, and I will throw it into the 카톡 room. Okay? All right. So let's do that. Okay. All right. Yeah. 그 중에서 그러니까 베스트니까 그 중에 16 학생이 풀었는데 요 그레이더 팀이 보기에 이 팀이 푸는 게 제일 멋있고 리거러스하고 좋다. 그렇게 하면 대부분 다 정답으로 와요. 집단 지성이지. 오케이. 자, 그렇게 하겠습니다. Yeah, and the relative entropy is non-negative. We have proved this the other time, and this relative entropy is the distance between two different distributions, right? It is bounded from 0, right? So it's a non-negative number. When you have equality, if and only if P is equal to Q, exactly, right? So proving this equality this way, let P equal to Q, and then showing dP and Q equal to 0 is easy, right? It's easy because if you do it right here, right? If Q is equal to P for all Z, then this ratio is 1, and then log of 1 is 0. So multiply with non-negative number with 0 is 0. Summation of 0 is 0, so it is 0, right? So going this way is easy, but going the other way, right? Only if part, proving the only if part is tricky. But we have done that tricky part right here, right? So equality if and only if Pz equal to Qz for all z, right? And this proof is very important for showing the information measure, right, as we will see it today, right? So remember that. All right, and the example calculations on relative entropy. So alphabet is given as a 0 and 1, and then you can think of two different distributions, px and qx, and then I have parameterized it by r, right? And for q, and then for p, I have parameterized it by r. So it is you can say that Bernoulli random variable with the parameter r, right? And then q is a distribution with a parameter s. So 1 minus s is q, another distribution function that x is equal to 0 that occurs with 1 minus s probability, and then q x equal to 1 occurs with the probability s, right? So we have a distribution P and Q. And then we can talk about relative entropy P and Q, right? P first, Q next. And then you apply that relative entropy formula. Basically, it is 1 minus R log 1 minus R over 1 minus S. And then plus R log R over S. Right? Just by applying it. And then if you do the switched version, let's say relative entropy between Q and P, then 1 minus S log 1 minus S over 1 minus R plus S log S over R. So in general, these two are different, right? Because the asymmetry in the formula. So dpq is not equal to dqp in general, right? In a particular case, it could be 0. For example, when r is equal to s, then it's obviously there is no distance between the two distributions because they are exactly the same. So it should be both equal to 0. Okay. And then when you utilize a particular parameter, let's say r is equal to half, s is equal to quarter, then dpq, if you use this formula and then use the calculator, then you will get 0.2075. And then dqp, 0.1887. So basically, order in the argument matters, right? In relative entropy. That's the message here. Okay. All right. It's obvious. All right. Relative entropy is non-negative. The other approach. Okay. There is the other approach. So suppose PZ and QZ are strict positive distributions. The same setting as before, so no zero probability masses. So let SP and SQ denote their alphabets respectively. So this one is exactly the same as previous page. Okay, and if the sum P log P over Q is equal to 0, then PZ equal to QZ for all Z. So this was the difficult part, right? Going this way, let P equal to Q for all Z, and then showing this one is easy, right? That the relative entropy is 0. Showing that is easy. But let the relative entropy equal to 0, and then show that P has to be equal to Q for all Z, right? That's a difficult part, right? Because it's it's not obvious, right? Because sometimes this ratio become greater than 1 or smaller than 1. Right? If ratio is greater than 1, log of 1 is positive. When this argument is smaller than 1, then log of argument is negative number. So summation of positives and negative numbers could end up equal to 0, right? Without having P and Q exactly equal to each other, right? It is possible. It's just common sense, right? But this one, in previous page, we have shown that already, that only if part is actually true, right? So, but that part, we can prove it one more time with a different approach. That's what this one is about, okay? So that's the relative entropy between P and Q, right? Okay? And then I'm going to say it is lower bounded by this one. Okay? Now I'm asking why. So this thing is a little bit of, you should give a little bit of a thought. Well, why it should be? Huh? So what is happening here? Is there some convex function argument here or concave function argument here? What do you think it is? Why can I say this is true? There is actually no argument. So here actually it is using a fact. This is a pure fact that log of x is greater than or equal to 1 minus 1 over x. That's what it is, okay? So there is no secret there. So it's just a fact. It's just fact, okay? Log of x 1 minus 1 over x. That's what it is, okay? Okay, so log of x, if you draw, goes like this, right? Log of x. And then 1 over x goes something like this. Okay? And if you invert and shift, basically, what we are saying here is this. This is 1 minus 1 over x. That's what it is. It's just a fact, okay? So equality happens only at this point, right? So when you substitute x is equal to 1, so here, this part here is 1, right? So log of 1 is 0, and then 1 minus 1 over 1 is also 0. So it only have a intersection right here, rest of them, this curve is smaller than that. So if you apply that, then we can get rid of this log and then replace it with 1 minus q over p, right? And then after you have done that, it is easy, right? Summation of p minus p times q over p. So p cancels with each other, top and bottom. Then it is left with q. So summation of q. Okay. Both, this is for SP, the set SP. So both of them SP. Okay. So this part could be smaller than 1, right? This part. Okay. But that can be, so this, this number is greater than when this number is greatest when this is exactly equal to 0, I mean exactly equal to 1. So it is lower bounded by 1 minus 1, which is 0. Okay? So this is another proof. So relative entropy is non-negative. One more time. We have done that. And now using this proof, we can make a powerful statement like this. So entropy is maximum when uniform distributed. Okay. So let ux be uniform distribution on the alphabet, okay? And h of p or h of x, but the h of x, the distribution is p, so it is equal to h of p, right? Which is the summation of p log 1 over p, okay? And then we artificially include u, right? So add log u and subtract log u. So if you add these two, it is 0. So I can do that without changing the equality. So once you have done that, basically you can pull out the u part, this part outside. Then I have this one, minus px log ux, and then plus for the rest of them, which is these two. So if I put them together, it is ux over px, right? Log of ux over px. Another typo here, I have a parenthesis like this one. I need to have down here as well. Okay, so after you have done that, we notice that this part is what? What can you say about this part? Log is a uniform distribution, right? So since it is a uniform distribution, does it matter when you change x? So inside this summation, this one is constant, right? So I can put it outside of the summation, right? And then basically that's this part, okay? All right? And what about this other part? This looks similar to relative entropy, right? But a little bit different, right? What is that? This, I can say this is a relative entropy between P and U, but as you can notice from here, it is inverted, right? So it should be negative relative entropy between U and P, right? I can do that, so I can do this. All right, relative entropy between P and U. Okay, so entropy of X, or entropy of this distribution that is given to you, right, is exactly equal to log of the size of the alphabet, right, minus relative entropy between P and U. What have you said in previous page about relative entropy? Relative entropy is non-negative number, so it should be equal to 0 or greater, right? So this is a number greater than or equal to 0, right? And then we are subtracting it from log of size of the alphabet, right? So maximum should be this one, right? Because we are taking away some positive number, right, from it. All right. And then what can you say about the distribution that achieves maximum point? That is the case when this relative entropy is equal to 0. When does that happen? When P is exactly equal to U, right, for all Z, right? So that means where maximum entropy achieved when P is equal to uniform distribution. Okay, that's another way of proving it. Okay. All right, so that's it for that part, and then we are moving forward. So entropy is maximum when uniform distributed. Right, that's the message. And then let's move on to another one. By the way, from this lecture and on, actually started from last lecture, we have the video available already, right? In previous year, 2020, when you go to Information Theory 2020 website, right? We have all these lecture videos available so that you can take a look at that, right? Okay, so if you miss something in class lecture, you can just take a look at that, okay? Exactly the same, okay? All right, and okay. Now mutual information is non-negative. We will prove this statement, okay? So mutual information is defined to be, so this is defined to be expectation or summation over pxy log pxy over px times py. So you have seen this before, right? Px times py, right? What did we call it? Product distribution. That's what we call it, right? When we use this for proving x and y independent, right? When pxy is equal to px times py for all x and y, right? Then we said that random variable x and y are independent with each other, right? Okay. Now we are doing this, okay? So now we can write this one with respect to the notation that we have just developed. What is that? Relative entropy. So this is, okay, P log P over P squared, right? So that's, this is relative distance between two distributions, which is, one is joint distribution first, and then product distribution next, right? Not the other way around, but this way. So the joint and product distance between these two distributions. Okay. Then now what can you say? Let's say if x and y are independent, right? Okay, that means this part here is ratio is 1 for all x and y, then it is equal to 0, right? That's the easy part. That's the easy part, right? Now, can you prove the only if part as well? Only if part is tricky part, right? Because sometimes this ratio can be greater than 1 or smaller than 1, right? If it is greater than 1, log of a number greater than 1 is positive, but log of a number less than 1 is negative, right? So sum of positive and negative numbers could end up equal to 0, right? So it is not obvious, right? In general, it's not obvious. So that's why we need that relative entropy proof, right? But we have proved that when you have equality, the top and bottom distribution should be exactly equal to each other for all x and y, right? We have done that in previous page. Oh, all right. Then basically, this one here is nothing but relative entropy between the two, and it is equal to 0 if and only if x and y independent. So we have done the proof, okay? And then using the expectation notation, we can write this way as well. This one is okay, right? All right. And then now mutual information between x and y can also be written this way, or h of y minus h of y given x as well. And then we will show one of them first, and then the other one you can do it on your own, right? So mutual information between x and y using the definition can be written this way: joint versus product. And then if you condition on y, joint distribution can be written as py times px given y, right? And then numerator py, denominator py can be cancelled with each other. So what's left is this one. And then if you apply this summation to the first one, right? And then you notice that that is conditional entropy, which is hx given y. And then for this part, you have a h of x. Okay? So h of x minus h of x given y. So mutual information between random variable x and y can be written as entropy of x minus entropy of x given y. Or if I condition this with respect to x, then you can do p of x times p of y given x, and then you can do the follow-up. Then basically px top and bottom canceled with each other, and then what's left is py given x, and then p of y. So in such a case, you can show that mutual information between x and y is equal to h of y minus h of y given x as well. So that's this part. H of xy is equal to h of y minus h of y given x. Okay? And this one is basically a measure how much one can tell about x knowing the other random variable. So knowing one random variable, how much you can tell about the other random variable. That's what it is. And h of xy and the h of yx, they are the same because it's a symmetric. Okay? All right. So this is just the definition. And the mutual information, we will consider a little further. So what's the meaning of this? Okay. So this, it is a measure. So it is again non-negative number. Okay. It's a measure, so it's a non-negative number. It talks about the amount of information about x we can have knowing y. So this is an ideal candidate for a communications problem. You send the x over a noisy channel, you receive y, and then knowing y as an observation, how much can you tell about the input? So that type of description is suitable with this mutual information. So suppose y is exactly equal to x. So there is a transmission channel, there is no noise whatsoever. So you send, that's what you receive. There is no noise added to it. In such a case, there is no uncertainty added during the channel transmission, right? In such a case, let's say entropy of x given y, or entropy of y given x, because x and y is exactly the same. Entropy is about uncertainty, right? There is no uncertainty, so it is equal to 0. So self-mutual information is entropy, okay? Because the conditional part is equal to 0, okay? So in this part, you can write as, I have it here. You can write this way, right? Okay. So self-mutual information when y is equal to x, so mutual information between x and x, that is equal to 0, okay? And in this case, let's say, suppose that y and x independent, then what happened? If you have an independent case, x and y independent, so knowing y cannot tell anything about x. In such a case, basically, this one is exactly equal to entropy of x, right? Okay, because y does not help for you to have any additional information about x, okay? So knowing y cannot tell anything about x, okay? And we can prove this using mutual information as well, okay? So can you show now I'm asking you a question so that, to see if you are following me or not. So can you show that if mutual information between x and y is equal to 0, then x and y independent? Anyone? Yeah. 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 So you are following it, right? Okay. All right. So we have this was the only if part that I was talking about when we proved the relative entropy between two distribution, right? So that is the only case. Your mutual information, the top part was what? Joint distribution. Bottom part was what? Product distribution. So this top and bottom should be equal to each other for all x and y. That is basically the definition of x and y mutually independent, right? Okay. So that's that, all right? Okay. And then what can you tell about, let's say, entropy of x and entropy of x given y? Now let me ask you, okay? Having said that, so far, we said mutual information is non-negative, right? When it is equal to 0, then x and y independent. We have said that. And then now I'm asking you, right? Number 1 or 2? Entropy, conditional entropy. This is the uncertainty of x. This is the uncertainty of x given y. Okay? So this is nothing else is given. And then, so in general, can you say number 1 is right or number 2 is right? Number 1. We have one person that number 1 is right. Any other person believes number 2?
I think either way is possible.
Oh, you think either way could be possible?
Yeah.
Oh, really? Okay. So 1 and 2 both possible. Okay, there's one vote. So this is option 3. One person voted for this. Is there any person believes in number 2? Minseok? Why do you